So this is the functional track, I believe, and the finance track. What I was quite curious about was to get a raise of hands of those people who are working in finance now. So that's not many. Okay, and who have ever worked in finance. That's okay, so we've pretty much got everybody covered now. And I'm going to be talking about across multiple languages, so hopefully that's good news for you. How many people here have used a functional language before? That's pretty much everybody, which is great. This is a great conference. Anybody not used a functional language? No, so one. Cool, today's your lucky day. Because I'm not going to do much functional today. So that's great. Okay, I think I've got a good idea of you guys now. My name's Phil. I work for a company called SimCorp, which are based in Denmark. We have offices in London. We're hiring. That's one of those inevitable things you have to say when you come up here. We're hiring for the Denmark office, so hopefully by the end of this, I haven't put you off too much. You'll come and talk to me and say, I want to work with you. My background, I've worked in finance for about 7 years, but I'm from video games, which seems to be quite common now. People want people who are cheap and work long hours, and that I fitted the bill really well there. Also people with some idea around performance. And this talk has come about from really a series of rants with Andrea Mignorski about things that I've seen go wrong and things that could go better, and trying to distill that all together. So, let's crack in. Going to start with horrible diagram, data-driven applications. Now, we've got on the left here a kind of long tail of pretty much loads of people around the world doing web applications with LAMP, or we could replace this with Ruby, and they have a database and some templating, and they put that together. And they have some sort of database here, and the database has all the data structure work for them, so they don't have to know anything about that. So that's probably a good thing. And it just kind of works for them. And then this is kind of what we see in finance and kind of line of business, enterprise line of business applications, is we have our database, but then we've got some layers in between it. And in effect, what I've seen most frequently in finance is it costs so much to have a server. By the time we've gone through all the red tape, it costs nearly £100,000 just to get through the red tape to buy a £1,000 server, that we don't want to have lots of servers. What we want to do is have some way of distributing the code, and the client's machine turns out to be a really good place to do all the compute. So, in effect, what we're doing, and you see this a lot in applications, is that we're driving the processing to the client, right? And in effect, the client is starting to do database-like things, and we're getting more and more data to the client, right? This is a great way of doing it, though, because the clients have lots of CPU power, and instead of having lots of expensive servers, we just push it over there. Which leads me to the next one. So you may have heard any sufficiently complex application probably has a half-baked, flaky version of Common Lisp built into it. And then the Erlang version, which is any complex distributed application, has a half-baked version of Erlang in it. There's another one, which is Green Cod's every sufficiently complex app has a half-baked database implementation. And that's where I'm starting from for this talk. So in effect, our performance of our application, we need to do database-like things in our apps, whether it be at the server or the client. And the reason for that is this. This is the timings for different actions on a computer. And if we take the right side column, because it's a bit more easy to reason about, CPU cycle, 1 second. And if we look at the stuff in the cache, when we keep it in the memory cache, it's going up close to a minute. But as soon as we miss the cache, 6 minutes, from 1 second, 6 minutes. So that's going to hurt, right? When we hit disk, it's 2 to 6 days. That's really, really bad, right? And now we're into months if we hit a slower disk. Months, right? And then going over the network, 4 years comparatively to 1 second. So clearly, if we want to go fast, we want to be in memory. And this is what's driving us to have our database-like operations in our high-performance systems in memory rather than off the database. Unfortunately, most of the systems I see don't have the data structures that you would expect to have if you were implementing a database. You're still using very rudimentary data structures. And that's basically what I'd like to talk about. And there is a reason for it. Most of my career has been about making things faster. But making things faster is actually what the customer wants. When you ask a trader, what do you want? Does he want it to look prettier? No, he wants it to run faster. And pretty much anybody buying anything on the internet would rather it moved quicker, although we spend a lot of time doing CSS style sheet changes. So performance is a feature. So we should write everything in C++, sure, clearly, right? That's the way to do it. So I'm going to give you a quick example. When I first started in finance, somebody had done an interview at an investment bank, and they'd been asked a problem about left truncated primes, which are primes. You remove one value from the left, and it should still be prime, right? So you need to generate these truncated primes. And this is the final version of speed between C++ on the left, C#, and F#. So F# being the more functional one. They're all basically the same. What this picture doesn't tell you is the earlier part of the story, which was when I first wrote the F# version, I asked the C++ guy to share his version. The F# version was twice as fast as the C++ version. Now, he did not believe this because C++ is fast. Then I explained that .NET code compiles just in time, so it is actually compiled code, it's not interpreted. But why was that faster? Well, actually the .NET collections, the .NET resize array, is about 20% faster than the C++ standard vector. The next thing, which is already significant, was the F# version just happened to use 32-bit integers because that was sufficient. The C++ one used 64-bit. The guy spent 2 weeks trying to reach the same speed as the F# version. In the end, I had to just tell him. And then it all panned out. But I guess one of the early points before I dive into showing you things is one of the most common things when dealing with performance is that people go, well, I'm using X, which must be really fast. And why? Why is it fast? What have you compared it with? Actually, the F# code, which shouldn't be faster, was twice as fast. If you don't compare, you won't know. And that leads on to another quick slide. Beware of these prefixes and postfixes. Okay, so I'll just let you soak that in. Some of these we're going to explain. This one we're going to do first. Quick is normally a good one. Fast, I generally think isn't. Fast, be really wary of fast and simple. That's usually the last thing they are. So, let's have a look at immutable lists. So, we're in functional land initially. We're talking about going beyond lists, and I'll move you on to more interesting things later. We have our immutable list. There's a definition in OCaml, and these are quite nice things. They're immutable, we can share them around, and they're laid out in such a way when we have a mutable linked list, we mutate the pointer. Here, we just point back, right? So the cost is no worse when we're adding than a linked list append, and we don't have the mutation property. So that's all good. So as an example, though, let's move on beyond addition. I don't know much about Haskell, but I know it's pure, and I've got a book called Learn Your Haskell for Great Good. And I found this thing, I don't know, is Tony in? No? I saw this thing, quicksort, in the book. I was like, oh, this is cool. I wonder if it's quick. So I'm gonna go and find that out. So I'm gonna do some code samples with F#. And the reason I'm gonna do it with F# is because I know it. And the other reason is there's this really nice function called time, which lets me, in the interactive window, find out how long things take, which is kind of useful when you're trying to do performance code. So I'm going to set the hash time, and every time I do an operation now, it's going to tell me how long it took. So that value is quite quick. Right. So what I want to do, I'll make a big list of numbers, and I'll write out that same sort function. And, oh dear. Okay, so we're already into Turing completeness problems at this point. So I know that's not going to work. Why don't we'll just give it a little hand this time. So I'm resetting that wasn't going to complete. If I give it a pre-sorted list, then maybe it will do okay, right? That's pretty cool. So it can actually sort a pre-sorted list of 1 million in just over a second. So that's pretty happy. But I wonder what the actual quicksort algorithm does where we do a sort in place. That's the kind of important thing about quicksort. So that's under 100 milliseconds. It's more than an order of magnitude faster, and that's actually sorted the one that's the other way around. So clearly, our immutable data structures are really cool, but in certain circumstances, it's not going so well. If we have a look at the standard library, so that's a third of the speed. So that's done a sort in 0.3 of a second. And actually, if we just convert to an array and back again, convert the list to an array, sort it in place, go back to a list, it's still 3 times faster than the sorting of a sorted list, right, using that mechanism. So there's something clearly, this immutable data structure is nice, but it doesn't seem to scale so well. And our arrays do seem to be doing quite well. So I'm going to spend a bit of time on this. So, well, it's short and a sort, but it's not quick. I think this is a quote from a friend of mine, John Harrop. I think we might be getting too puritanical about purity when it comes to speed. I think the purity is really nice, when speed's not important, but maybe, we would like our things to actually end at some point, to actually complete. So, next thing we're going to look at is laziness, another property that we see in pure functional programming languages and also in our standard languages. So if you're using JetBrains' ReSharper product and you've got a for loop, it will tell you, I see you have a for loop. Why don't I turn that into a link expression? Why don't I turn that into a higher order function for you? Because that'll be cool. So that's nice. And it becomes declarative. Unfortunately, it also typically can end up being 15 times slower or more. So it is prettier. So some guys in Greece, a team called Nessos, have a link optimizer that take the declarative high-order functions and turn them into imperative statements on the fly for you. And you can get speed-ups of up to 15 times. So if we start at the bottom, we have sum of squares, 5 seconds with a standard link. Using it being unrolled to 4s, it's less than a second. So very big improvements from not doing declarative. But the thing I kind of like about this is that you write it declaratively, and the compiler works that out for you. It turns it into a for loop, so we can still do our nice code, and we can move forward. Another library they've got is streams. So anybody using Java or Scala? So Java 8 has this new streams library, and actually it's pretty cool. It's the link library pulls data, streams push, and in a number of scenarios, streams are significantly faster than link. So we're kind of jealous of that. You've come late to the party in Java, and you've got faster systems. So again, the Nessos guys have a paper, Clash of the Lambdas, and a library. And if we have a look here, this is standard sequence, and this is the optimized sequence using, in effect, a stream, and you can see the time is significantly lower. So this is all good. So while I was tweeting about how great this was, there's another push mechanism called Reactive Extensions. And so how does that compare? Somebody said our numbers are hard to beat. And we've already talked about not checking other versions. So I had a quick check. So the reactive extensions doing sum of squares was nearly 3 seconds, right, to do a certain number of sum of squares. Reactive extensions use something called an iObservable interface. This was first in F# in about 2006. So I had a look at the original implementation from F#. This was from 2010 onwards. And, oh dear, the naive F# implementation is 6 times faster than that one. So it's not that hard to beat. And then if we look over here at the Nessos Streams version, it's 0.1 of a second. Oops. So about 20 times faster. So nice thing about this is obviously streams could be fast, but also I'm just trying to reinforce the point that if you don't check against another implementation, you might end up with egg on your face when you say your thing's really fast. And a little bit of Star Trek for that. But the thing I keep seeing again and again with the performance is not testing against multiple implementations, setting out to confirm your bias, and not even bothering to instrument and profile your code. But I'm sure all of you do that. Good. Okay. So we've said there's some problems with our lists. Let's have a look at lookups. They're our dictionary. So this is from an article by Yan Kui, and he's looking at the time it takes to add 1 million items, followed by the amount of time it takes to traverse 1 million items. Now, arrays are really good at, resize arrays are really good at this. So this is the benchmark, 1 times. Again, 1 times.
And this is with what technology?
This is on .NET, but you would get a similar thing. It's just an array, Java, C++. But good question, thanks. Now, here we've got the F# map, which is an AVL tree. basically you'll get the same speed again. The AVL tree is an immutable map. It's 244 times slower at insertion, which isn't too surprising. Yeah. The dictionary, which is a hash table, that's actually quite reasonable. And then lookup-wise, the AVL tree is actually not too bad, but the insertion's really expensive, and the dictionary's doing better. So what we can see here is if we want to go fast, all we need to do is turn on our mutable collections, right? Now, there's a lot of functional people in the room. I think, for me, as I say, I like to have my collections immutable by default. But a lot of the time, I'm actually holding my state inside an agent, right? So nobody else can see it. It's completely safe. And in that scenario, using mutable collections and getting orders of magnitude performance improvements is pretty sensible, right? So, oops. But I've said that about arrays. What I want to do now is completely disprove everything I said again. So, we're going to set our value out to 10 million. I'm going to create an array, 10 million items. That's taken just under a second. And I'm going to remove from the back. And that's taken just over a second. That's pretty good. That's 10 million items in, 10 million items out. I'm going to create a new one. And this time, I'm going to remove at the front. Now, I've seen this in production systems. People have come to me and said, the thing's just hung, right? And you're like, but I can't work it out, you know? And typically on Java and C#, they have things called lists, which are actually arrays. So people don't even know what they're dealing with. So let's try this out anyway. So I'm going to remove from the front on 10 million. And I'm not going to hang around with this for long. I've never actually got to the end of this one. I think I'd probably have to leave a computer on for a year or so. So what this is doing is every time we remove from the array, we pull all of the items back one at a time, right? This is not a good thing. Now, pushing them at the back was really, really easy. So let's stop that, because that's just taking too long. The other problem we've got is quite often in trading scenarios, in a lot of scenarios, we need to insert into the middle, right? So what I'm going to do is set up a scenario where I create 10 million items. Oops. And I've managed to, let me just do that again, insert 100 items into my 10 million item list. And it's just taking under a second to insert 100 items. So that's not going to work either. It's as bad as a removal problem. So the next thing I might go, well, what about a linked list? Because it's quite easy to remove something from the chain. I don't have to copy, right? So let's try and add 10 million items. Into a linked list. Oh, bugger, that doesn't even finish. So what we've got here is we've got something that's really good at adding to the end again with the array. It's very good at traversing, but absolutely awful for random insertion and removal. and the linked list is dead because I can't even get 10,000 items into it before you guys get bored. So that's a dead one as well. So we'll come back to those. So at the moment, they're looking like dead ducks, right? But maybe there's something we can do with them later. That's where we're going to get to. So the next thing I wanted to show you was, we've got our dictionary. We've looked at arrays. We've got our dictionary. Now, one of the interesting things I found in .NET is a hybrid dictionary. And the hybrid dictionary has a list and a hash table. And this is kind of cute because traversing small amounts of data seems actually quite fast. So this green line is the time it takes for the when it's traversing a linked list. So for small n, insertion and traversal is fine. And as we go up, it ends up being rubbish. But actually, a lot of the things we have are small dictionaries. And so traversal is easier. So I just quickly wanted to show you that. Because it is linked to what we're trying to do. So I've got a bunch of key value pairs. Oops. Oops, sorry. This is the hardest part of presenting. Please let me know. Switching between PowerPoint and the desktop's really painful. Okay, sorry, let me show you that again. So I'm going to set up a scenario where I look up to 50 items in a collection. And I'm going to compare that against doing it in a dictionary, against a hash table. So let's just run that a few times. So lookup's about 30 milliseconds. Create a dictionary. And we'll do the same lookup. Okay, so the brute force lookup over 50 items, just going across an array, is about 6 times faster than doing the hash table. Right, so what we're getting here is we're getting data structures are really cool. The dictionary is much faster than the AVL tree, but actually for small n, these arrays seem to be incredibly fast, right? The processor seems to love going in straight lines, right? Now, we could use this, and that's where we're driving towards, but actually, if we remember back to the speed of the CPU, the amount of time it takes when we go out of the cache is about 6 minutes compared to 1 second when we're on the processor or in cache, right? So it kind of makes sense. If we keep everything local and we're in cache, it's going to be really fast. And that's kind of where we want to be driving. We don't want to have lots of data spread out across the system. We're 6 minutes against 1 second. I know which I want, right? So let's go back in. That. And what's that? An example of that is in databases. So one of the databases heavily used for time series data in finance is KDB, and that uses a column store. If we use classical kind of relational store with rows, every time we want to check each date, we've got to go all the way across. So we're missing cache values, right? If we store all of the dates and we need to compare the dates, they're all in a line, our cache affinity is beautiful and we go significantly faster. And we can do, KDB's in memory, we're in memory because we want to go fast. This is all really important. I actually wrote a database for Tesco.com back in the turn of the .com boom, and they had a database. It was taking up to about 15 seconds to get the round trip from the database because the database is so heavily loaded. I wrote a column store database, and it was for the read-only data, and we managed to get the round trip down to around a millisecond, right? So this really does work. So we're using column store values. Okay. Data structures. If we look at our example of insertion and removal, if you have a text editor and you've got your million lines of C# code or Java code, and you press a button, it will try and insert into an array, right? And that you're waiting for 2 hours for it to do that insertion. One of the common data structures for this is a rope, hang by the rope. And the idea there is, instead of moving everything across, we create a tree. We say, this 500,000 is one side of the tree, and the other 500,000 is the other. And we can insert our new character C between the 2 points, right? So instead of moving 500,000 points over from our million, we just create a simple tree which has our new value and the left side of the large string and the right side. And eventually with the rope, if it gets too complex, we just rewrite out the whole string. But it means that we've basically got almost instant insertion inside, say, 1 million items, right? So this is insertion time. This is the rope. We like this one. This is the green one. And the red one is string builder, and that's a standard string. So this is quite nice. Typically, we don't write a lot of word processors in finance, so we're not going to spend too long on this one. Next one I wanted to show you is an unrolled linked list. Anybody seen one of these before? Got a few nodding heads. So we've said that the long arrays are really bad, linked lists are really bad. What if we put them together, put two really bad things together, would we get something good? And usually not. But in this case, you do. So the problem with linked lists is that you have a link and the item, and that's quite heavy, right? So what you do with a unrolled linked list is you have a link and a bunch of items, right? And what we can do then is that bunch of items, that's all very local, it's an array, okay? So we've got great cache affinity. We're going to be in memory once we've traversed to it. And then the fun bit comes when we do an insertion. Let's say that link is full. We've got 40 items in it, and we insert one. All we need to do is we don't need to move 1 million items up. All we need to do is we split that node in half and add a new chain, right? So that means that you can literally insert into 1 million items again with virtually no cost. Now, once you've done one split, the next time that you insert, it's already split, so the insertion's free. And what it turns out is that probably about 99% of the time, depending on how big each of the buffers are, you've got no allocation whatsoever when you insert and minimal copying, only the size of the range, which is hugely fast. I'm going to give you a quick example in code in a minute. But I was working on a system for a front office system, and we were taking about 100% CPU to deal with 100 trades per second. I replaced it with the unrolled linked list, and we went to 10,000 trades per second on 0% CPU. Right? It didn't actually measure on Task Manager because it was less than 0.3% CPU. So I was kind of freaked out for a while because you don't normally get to 0. And then I put some delays in it and realized that there was like a threshold where it would notice that there was CPU going. But this is kind of cool. So this is kind of database-like. And the lovely thing here is if you need to do traversal, it's all laid out nicely for you. So if I needed to slice out 50 items to display in a list halfway through 500,000, it's all laid out reasonably nice for me. The only downside with this is that when I traverse, I have to compare the last node of each one. So if I start to get into the hundreds of millions, then that traversal cost is going to cost more. So maybe we want something a bit better. But let me just show you that data structure, because it's nice. Have we got any OCaml programmers here? Oh, one. Brilliant. F#. Oh, lots of hands. That's great. So this sample will be in F#, but the code's actually just copy and pasted from OCaml. So if I go back to that sample where we're doing the insertions, and instead of using an array, I used an unrolled linked list. Oops. So let me just get my session going. Okay, so we were about nearly a second to do those insertions on the array, just 100, right? And we're around 30 milliseconds with the unrolled linked list. So basically, it feels like we're almost at the panacea point, right? We're feeling quite happy. And for most practical purposes, this would be enough. The unrolled linked list implementation is fairly trivial, so 200 lines of OCaml nail it. I'll just show you it's not much different from a linked list. You have a node, and instead of having an item in the node, you have items, right? Pretty easy. So this is a really nice, easy switch to get incredibly good performance gains. And then as some additional optimizations, we store the first and last items so that we can quickly insert.
And is the real key to that breaking up into pieces that can then be kept in the cache?
Exactly. The key, yes, good question. The question was, is the key to this breaking up the pieces so they're in the cache? Yeah, it's a huge part of it. So we avoid all the huge copying, right? When we do copy, it's only in a very small fragment. When we do traverse or read, it's all in cache, right? Now, typically what you would do is set your page size, your items array, to fit neatly within a page size in memory. So your CPU's loading in a page, right? And so basically you take one cache miss, potentially, and then from there on, it's all happy cache. And we're all in the 1 second area instead of the 6 minute area. So it is really beautiful for that. So we've got this lovely affinity by using an array. The breaking of them, when we do have to insert and we've already spilt, is still quite a lightweight operation. Okay. So, next. Oops. The next type is a B+ tree. And actually, so you're probably going, well, this list thing is a bit sucky because, we have to go from one end to another, even though it's actually relatively fast because we're in the cache. But what we really want to do when we want to get to the end of like 100 million items is we want a tree. We just want to go down the tree. So all of your standard databases, Oracle, Sybase, SQL Server, you name it, use a B+ tree, right? And a lot of in-memory databases, CouchDB, use B+ tree. Now this is actually only a very small change over the unrolled linked list, so I was building up to it. What we do, it's slightly different to a Btree, standard Btree, in that we actually hold all the values in the nodes. So I'm showing you a Btree here, move on to the B+ tree. But this splitting behavior that we had in the unrolled linked list, which is our kind of key point, holding everything in a cache, our Btrees do that. And again, the implementation isn't that hard. In the 90s, people tried to use T-trees when caches were smaller, but Btrees have been found to be faster with modern hardware, or B+ trees. So don't just ignore that. Ignore the T-tree thing and go straight to the Btree. But yeah, basically, you construct a tree. When you fill an area, you split and you push the values back up, and that's all there is to it, right? And if that's filled, you split back up. So it's a very small adaptation over the unrolled linked list. Okay? So if you want to go fast, you want to be mutable, right? And you want to be able to get affinity on memory, and you want to be able to scale to huge numbers. And these data structures are basically how databases achieve that with disk, sometimes with memory. And you can have those in your own programs. And we've solved everything. We've solved our database problem. So the actual data structure you'd want is a B+ tree. I found this along the way. This is probably a bit gushy. But one of the most beautiful and useful inventions of computer science. And nobody's using them. Well, everybody is using them because you're using them in a database, but you're not using them in your applications. If you do, you're going to go really fast. So I think I'm about out of time. Let's go out of time. So I'll quickly sum up. I've gone on and on about speed and mutability. Please don't get me wrong. Prefer safe and simple defaults. Prefer immutability, right? Because most of Pareto's rule, most of your code is not performance critical. But when it is, when you've profiled your code and it's going really badly, or you know you've got millions of items to traverse, switch. So profile. Mutable arrays are fast. Build your data structures from arrays. And be pragmatic. So that's pretty much all I've got time for. There's on my GitHub, there is a implementation of unrolled in OCaml, which you can copy and paste into F#. There's actually an implementation in Scala already. I think it's quite common data structure usage there. And I will be publishing my Btree, B+ tree shortly in the same place. There's my Twitter and blog. Any questions? One question at the back.
Thanks, I thought that was a great talk. I'm not a Windows guy, so...
Right, sorry.
I just wondered if you could talk maybe a little bit about how you go about profiling the application, how you work out where the sweet spots are, what you do to
Yeah.
investigate, things like that.
Cool. Yeah, so the question was, how do you go about profiling? Because I keep saying you should profile. So on the Windows stack, and I think it's beta similar for JVM, I use tools like YourKit, which you have on the JVM as well. The built-in Visual Studio one. I use any profile I can get my hands on because often you get slightly different nuanced results. That gives me a general feeling, but I don't trust anything ever. So I will then potentially, once I've found a hotspot, the act of viewing something usually changes it slightly, so I will put in some instrumentation directly in the code to make sure that it is doing that time in the real world scenario. And then from there, what I will do is pull out the section of code that is dodgy, and I'll run it inside a REPL, and I'll time it in different scenarios, and I'll try different implementations until I get where I want to go. So at that final point, I will do the REPL like I did in the samples. And for me, that's quite important.
What was that tool you mentioned,
Your kit is pretty much my favourite profiler for .NET, but it's also available for the JVM. Cool, I think I've been told I'm done. Thank you very much, and cheers.